Organic oxidation. Let's be honest, for a lot of chemistry students, those two words bring on a headache. It feels like this giant, chaotic mess of reactions you just have to memorize. But what if I told you there's a simple, predictable rule that governs all of it? Well, today, we're going to find that rule.
I bet you've stared at pages and pages in your textbook. You know, alkanes turning into alcohols, aldehydes becoming acids, and you've tried to just cram it all into your brain for the next exam. But that's the hard way. It completely misses the big picture. The real secret isn't about memorizing what reacts, it's about understanding how it reacts.
So, how do we do that? How can we just look at a reaction and know what's going to happen? Well, the trick is to stop focusing so much on the molecule you're starting with and instead focus on the chemical tool you're using to change it. Once you get that, you can predict the outcome every single time. No flashcards required.
Okay, this right here, this is the oxidation ladder, and it's basically our map for this entire topic. It just shows the progression, how a carbon atom gets more and more oxidized as it picks up more bonds to oxygen. You see, we start at the very bottom with a simple alkane, and we can climb up to an alcohol, then a carbonyl, then a carboxylic acid, and right at the very top, we hit carbon dioxide.
So here's our game plan. First, we're going to crack the code that controls these reactions. Then, we'll put it to the test on some really simple hydrocarbons before we move on to trickier molecules. And finally, we'll see how all this knowledge comes together to form a practical toolkit you can actually use.
All right, so what is this secret code I've been talking about? It's actually incredibly simple. The power to predict what's going to happen doesn't really lie with the molecule you're oxidizing. It's all about the strength of the oxidizing agent you use.
This right here is the key to everything. Seriously, if you remember one thing, make it this. Think about it like this. A weak oxidizing agent might just gently nudge a molecule one step up our ladder, but a really powerful one, it can launch that same molecule straight to the top floor in one go.
And this table, this is your cheat sheet. We can basically sort all these different oxidizing agents into 4 categories. You've got your extreme ones like acidic potassium permanganate that just go all the way to the end. Strong agents will push the reaction pretty far up the ladder. Weak agents, well, they only have enough juice for a single step. And then you've got these cool controlled agents, which are designed to stop at a very specific spot.
Okay, enough theory. Let's actually see how this works. We're going to start with the simplest organic molecules out there, the hydrocarbons, and see if our new map can actually guide us to the right product.
We're going to use good old methane as our guinea pig. By keeping the starting molecule the same, we can really clearly see how just changing the strength of our tool, the oxidizing agent, completely changes the final product.
First up, let's bring out the big guns. If we hit methane with an extreme agent, like acidic potassium permanganate, it's like taking an express elevator straight to the top of our ladder. It just blows past all the intermediate stops and goes directly to carbon dioxide. Complete combustion. Done.
Okay, now let's dial back the power just a little bit. We'll use a strong agent, like aqueous potassium permanganate. The reaction is still really powerful, and it climbs way up the ladder, but it stops just one step short of the absolute top, giving us methanoic acid.
And finally, let's be really gentle. A weak agent like basic potassium permanganate has just enough energy to do the very first, easiest step on the ladder, turning that alkane into an alcohol. It makes methanol, and then it stops. So look at that. One starting molecule, 3 totally different products. And the only variable was the strength of our tool.
So far, so good. But we've only been looking at single bonds. What happens when you throw a double or a triple bond into the mix, like you see in alkenes and alkynes? Well, this adds a really fascinating new twist to our rules.
This is a huge deal. It's a critical difference. With alkanes, we were just kind of modifying the molecule. But with alkenes and alkynes, a strong enough agent doesn't just modify, it breaks. It actually targets those weaker pi bonds and can physically snap the carbon chain right in half.
Let's just look at ethene. A weak agent will gently open up that double bond and add a couple of alcohol groups, but it leaves the carbon backbone totally intact. This is the classic Bayer's test. But if you use a strong agent, it's not gentle at all. It's like a demolition crew. It shatters the entire double bond, breaking the molecule into pieces and then oxidizing the fragments.
So, this is all cool theory, but why does it really matter? Well, because when you understand these rules, you can use these reactions for more than just making new molecules. You can use them to figure out what molecule you have in the first place.
Check this out. It's pretty slick. Let's say you have a mystery alcohol. A weak oxidizing agent becomes an amazing diagnostic tool. A primary alcohol? It'll oxidize to an aldehyde.
A secondary alcohol, it becomes a ketone. And a tertiary alcohol, well, it won't react at all. Why? Because that central carbon doesn't have any hydrogens left to remove. It's a super simple, super effective way to tell them all apart.
And we can play the exact same game to tell aldehydes and ketones apart. Aldehydes still have that one CH bond that's pretty easy to oxidize, but ketones, they don't. So if you add a weak agent like Tollens reagent, that aldehyde will happily oxidize up to a carboxylic acid, while the ketone just sits there and does nothing. It's simple and it's elegant.
Now, this idea of controlled oxidation is where chemists get really clever. Take the Etard reaction. The goal is to turn toluene into benzaldehyde. If you used a strong agent, you just overshoot the mark and go all the way to benzoic acid. But by using this really carefully balanced controlled agent, you can stop the reaction exactly where you want it. It's like precision chemistry, using a chemical scalpel instead of a sledgehammer.
So let's just recap the awesome set of tools we put together. We now know how to use specific agents to tell primary, secondary, and tertiary alcohols apart. We can tell aldehydes from ketones. We can even use a strong agent to break a big molecule and figure out exactly where a double bond used to be. And we can use controlled agents to build specific products with total precision. So, let's bring it all home. Organic oxidation. It's not the chaotic mess it seems to be at first glance. Not at all. It is a predictable, logical system. And the secret to unlocking the whole thing is just to shift your focus away from the starting molecule and onto the oxidizing agent. When you understand the tool, you understand the outcome.
You know, this way of thinking, of looking for the underlying rule instead of just memorizing a million different outcomes, is one of the most powerful skills you can have in science. So my question for you is, now that you've got this map, what other confusing topic in chemistry could be unlocked if you just looked for its oxidation ladder? Something to think about. Thanks for joining me.